Hello, I am Juyong John from Arise Lab of Handong University, and in today's talk we will be discussing about detecting subtype inconsistency error by unit test cross-checking. This is a brief overview of today's talk. In order to solve the test oracle problem, we propose a method of using the common features of the sibling class as test oracle. Even though sibling classes are not identical to each other, there are some common features in their behavior, and we are using that as a test oracle. So for example, under the category of bee, there are three types of bees: mason bees, honeybees, and bumblebees. We here added a new type of bee called carpenter bee. We want to see if the carpenter bee is correct for a bee. So we compare the carpenter bee with the three of the sibling bees. And we here notice that carpenter bee has three wings unlike the other three bees, which is wrong for a bee. The technique detects inconsistency errors by cross-checking the test results of the sibling classes, using the idea that a test case should pass in a class when it passes in the most of the sibling classes. So this method uses automatic test suite generation tool to generate unit tests for each of the sibling classes. And using the generated test, we execute the tests on the sibling classes and compare the results to detect inconsistency errors. Using the technique, a case study on Apache Commons collections was conducted, and as a result, we found two types of inconsistency bugs. Before we begin talking about the technique, we first would like to define some key terms used in the talk. The first term is subtype polymorphism, which allows the children classes maintain the structure and the semantic of the parent class when referring to the parent class. So below is an example of the subtype polymorphism, and under the parent class num, there are two children classes, int num and long num. The children classes maintain the structure and the semantic of the parent class. So in terms of structure, the return type and the argument type of the method max value is kept as it is defined in the parent class. And in terms of semantics, both children classes return the larger number between the argument and the object. The second term is subtype inconsistency error, which is a type of error that occurs when the semantic or the structure defined in the parent class differs by which child class the parent type object belongs to. The structure inconsistency error can be detected by the type checking of the programming language, like Java interface, but semantics inconsistency error can only be detected by testing whether the function works as it is intended. This shows an example of semantics inconsistency error. The method divide defined in parent class num divides the inner field with the value received through argument, and when the argument value is 0, it throws illegal argument exception. For child class int num, the method divide throws illegal argument exception when the argument is 0, like it is defined in the parent class. But in the class long num, the method divide does nothing even when the argument is 0. So when the field is divided, the arithmetic exception is thrown by the Java library. So to detect the semantic inconsistency error, a test oracle that depicts the requirements of the common behavior defined in the parent class should be written and be tested throughout the children classes. But since creating test oracle for the common behavior takes a lot of time and effort, we here introduce a new method by using the automatically generated test cases of the sibling classes as test oracle. So we will see how this works on the example previously shown. So on the child class int num, we generate test case automatically using the automatic test generation tool. And on the generated test case, we can see that the method divide throws illegal argument exception when the argument is 0. We change the instance of int num to long num and execute the test on long num. The test fails and thus the error is detected. We will see how the technique works in each of the steps. So the proposed technique uses the given children classes that share a single parent class and returns the test cases that are likely to detect inconsistency error with each of the test cases' suspiciousness score. The first step of the technique is for a developer to write an adapter class for each of the child class. The adapter class is needed to make test case generated in each class be executable in the sibling classes. There are two reasons to why the children classes may be incompatible to each other, and the first reason is that the class constructor may require specific parameters that are not required in the sibling class. And the second reason is that unit tests generated in the child class may include methods that are not defined in the parent class, but only in a certain child class. The next step of the technique is to generate test cases on the adapter class using automatic test generation tool. In the suggested technique, EvoSuite was used for automatic test generation tool, and we used only the tests that pass in the class that the test was generated from. After that, the generated test cases are executed on the sibling classes, and the result is recorded as pass or fail. And when the test fails, the exception type and the occurred location is also recorded. And for the final step, the test cases are prioritized in the order that are likely to detect inconsistency error. And the priority of test cases is higher when first the number of sibling classes show inconsistent result with the original test result is higher, and in second, when the smaller number of test cases that is generated in the same class has failed with the same exception type and same exception occurred location as the target test case. So the first standard is based on the idea that when more sibling classes show an inconsistent behavior about methods defined in the parent class, it is likely to be an inconsistency error. And the second standard is based on the assumption that when inconsistent result is shown globally throughout the test cases, it is likely that the inconsistent results are due to unique behavior of the class and not the inconsistency error. We will see how the test cases are prioritized using an example. The table shows the result of generated test cases on each of the child class. With the first priority measure, test cases that showed inconsistent result the most are test 3, test 5, and test 6, because in two of the sibling classes, the results are inconsistent. Before computing the second priority measure, we will look at the source code of the four tests. The test 3 checks whether the method divide throws arithmetic exception when the given argument is 0. When the long num instance is changed to double num, the test throws illegal argument exception and it shows inconsistent result. The test 4 checks whether the long value and double value of an object is same, and this test shows consistent result for double num. The test 5 and test 6 checks whether the property of the floating point number is kept. And when the double num instance is changed to long num, the test fails because long num does not keep the floating point information. The table shows the result of test cases on each of the children classes. In test 3, the int num and long num fails due to illegal argument exception on line number 5 and 7. But on test 4, all three classes passes the test case. For test 5 and 6, in int num and long num, the test fails due to assertion failure. Here, it is shown that the uniqueness of double num that deals with the floating point numbers is shown throughout the several test cases. So therefore, according to the second priority measure, test 3, which has the smallest number of tests with same exception type and location, has the highest priority. To verify the suggested technique, we conducted a case study on an open source project, Apache Commons Collections 3.1. And the target program was the children classes of Abstract Collection Decorator, which are fixed slide list, lazy list, and set unique list. We also added the growth list, which was added in Apache Commons Collection 3.2. For a automatic test suite generation tool, we used EvoSuite, and when generating test cases for each of the test classes, we limited the test generation time to 30 minutes. And as a result, total 291 test cases was generated from 4 of the children class. The table shows the result of the case study. In the second column, it shows the number of generated test case for each of the child class. And in third column to sixth column, it shows the number of test cases that show inconsistent result between the original class and the result in 0 to 3 sibling class. Among the 291 generated case, 149 tests had at least one inconsistent result. And after ordering the test case by the parity measure, we checked whether the test case detected an actual error. And as a result, we found that 25 test cases show inconsistent result because of 2 real bugs. The first bug was detected on 4.5th test case on the ordered list, and the second bug was detected by the 10.5th test case on the ordered list. The remaining 124 tests showed inconsistent result due to unique behavior of the. So this is the description of the first bug, and the test that revealed the first bug called add all method with the index value of -1. And on the set unique list, this test successfully terminated by adding the linked list at the end of the list. But on lazy list and growth list, the test throws index out of bounds exception. When we examined the source code, we found a bug on set unique list that adds the object received at the end of the list regardless of the location the argument is given. The test case that revealed the bug was found in the 4th or 5th test case in the ordered list. To summarize the talk, we have suggested a technique that uses the commonness of children classes as to detect the inconsistency error, and the technique was applied to children classes of open source project of Apache Commons collections, and we found 2 types of bugs. And as an extension of the research, the technique will be applied to more artifacts to validate its effectiveness, and an adapter which is written by a developer in the current version of the technique will be generated automatically to increase the utility of the technique. So we also plan on using the different test automation tools such as Randoop that generates tests by randomly enumerating method sequences and comparing the result of Randoop with that of EvoSuite. So this is the end of the talk. Thank you for listening.